In this lesson, we are going to take these polynomial functions, which we've now learned how to factor completely, and we are going to draw them. So you have already learned how to draw linear functions. You've already learned how to draw quadratic functions, which are parabolas. And now we're going to look at drawing these polynomial functions, which might have a degree 3 or degree 4, or maybe a few degree 5, but nothing beyond that. So the key when you're sketching graphs of these polynomial functions is that the first step is that you must factor the polynomial. Factor it completely. So you're going to use synthetic division, you're going to factor it completely. Now, once we have it in factored form, just like when we were dealing with quadratics, so as you should recall, when we were dealing with quadratics in factored form, so let's say, for example, something like that, we knew that the x-intercepts were at x equals -4 and x equals 2. Those were our x-intercepts. Now, in this case, we use the factored form the exact same way. That factored form is going to give us the x-intercepts on our polynomial graph. The only thing that's different is that sometimes you are going to have repeated factors. So now that we're dealing with, for example, we could have a polynomial of degree 3. So we might have something like this, where the factored form has some factors that are repeated. So you'll notice here, x plus 3 and x plus 3 is repeated. What we need to remember, or learn about in this case, is that the graph is going to behave differently around this x-intercept and this x-intercept, because this is just an x-intercept of 2. This is an x-intercept of -3, but around here, the behavior of the graph actually changes. So I've summarized that for you. Here, it says if a factor is repeated an odd number of times, the graph will cross the intercept. So that is, for example, if it's repeated just once, or 3 times, or 5 times, any odd number of times, the graph is just going to go through that intercept and continue on. Now, if it's an even number of times, and most commonly what we're going to see is factors that are repeated twice, so that means 2 factors that are the exact same, it's going to bounce off that intercept. So it's going to hit the intercept and then turn around. Now I've got a little note on the side of your page here, and it says if the multiplicity, that's what we call these, the number of times that a factor is repeated is called its multiplicity. If it's 1, it goes and crosses the intercept, it just goes straight through. If the multiplicity is 3, this graph actually goes straight through, but sort of changes in direction. And we're going to do some examples of these so you'll see what that looks like. But that's just a little side note to keep in mind. After you do that, you've got your x-intercepts. Then you're going to go way back to what we learned about in the first lessons. And that was the end behavior of graphs. So remember, we use the leading coefficient and the degree to determine what quadrant a polynomial graph will begin or end in. Then we can find the y-intercept, and then we can use all of that to sketch the graph. So this first example is already factored for you, which is actually the bulk of the work. So this is already factored. This, we have x minus 1 times x minus 1 times x plus 3 times x plus 3. That is the factored form. So I know that my x-intercepts are x equals 1 and x equals -3. And they're both repeated twice. So they have an even multiplicity, meaning the graph is going to bounce off of these 2 intercepts. So these are your two intercepts, and you'll see here it bounces off, meaning it hits the intercept and then turns and goes back up. Same here, it comes toward the intercept, hits the intercept, and then bounces back up. Next, you need to figure out where this graph begins and ends. So this is an even degree. If I multiplied x times x times x times x, I would get x to the power of 4. So it's an even degree, a degree of 4. And the leading coefficient would be positive because this is positive x, positive x, positive x, and positive x. There's nothing there that would make that leading coefficient negative. So this means, if you go back to your chart from the beginning of this unit, this means it goes from quadrant 2 to quadrant 1. Finally, before I drew this line, I also found the y-intercept, which means you just plug in x equals 0, so 0 minus 1 squared times 0 plus 3 squared, that equals 9. So what I would do is I would sketch -3, 1, and y equals 9. You then know that you're starting in quadrant 2 and ending in quadrant 1. So this is just a sketch. You're going to start up top. You're going to come down towards your intercept. We know that it bounces off the intercept, so you're going to turn directions and go back up. Then you're going to loop down, make sure that you go to your y-intercept. You know that the graph must change directions in the middle here, because there's no other way to go from this point bouncing up and then back down to this intercept. And we know it crosses through y equals 9. So I go up, cross through y equals 9, and then at this intercept of 1, it's an even multiplicity, so again, it's going to hit that intercept and then bounce up, which leaves us in quadrant 1, which is what we know that the end behavior has to do. Now you'll see I put a little note here saying you don't have to solve for what this maximum is. These graphs are going to be symmetric, so I've tried to make this as symmetric as possible, but you don't have to find this absolute maximum. That is actually something that you will learn how to do in calculus. So just a side note, your domain in this case would be XER, or negative infinity to positive infinity, and your range would be 0 to infinity, or y is greater than or equal to 0. If we look at another example, example 2 was not factored for you. So you'll notice in example 2 that I actually had to factor it first. Now, remember to factor this, you start by plugging in all of the factors of 6. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now luckily in this one, when you plug in f of 1, you get a result of 0 right away. Because I know that 1 is a factor, I can use that as my a value to do my synthetic division. When I do that synthetic division, here is my partially factored form. So x minus 1 times 2x cubed plus x squared minus 13x plus 6. But now I still have a cubic function that I need to factor. So I actually need to do this whole process over again using just this polynomial. So again, that constant is 6 again. So I'm going to try and plug in plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Now for space's sake, I didn't write those all out, but p of 2, when you plug in 2, gives you a result of 0. So we can use an a value of 2 in our synthetic division. Remember, bring down, multiply, add. And then I get a nice quadratic function here, which factors nicely, and I'm left with my entire function fully factored. Now don't forget, up here I had x minus 1 as one factor, and then this was the polynomial that I was simplifying further. So this x minus 1 is from up here, and then this second half of it is this second division that I did. So there's 4 factors in this polynomial. So again, we know that my x-intercepts come from these factors. So x equals 1, x equals 2, x equals 1/2, and x equals -3. These are all have a multiplicity of 1, meaning they all just cross through. It means your graph is going to approach it, cross through the intercept, and keep going. I also know that my leading coefficient is positive because it's a 2, and this is degree 4, so even. So again, we're going from quadrant 2 to quadrant 1. And finally, my y-intercept, when you plug in x equals 0, or just look at your constant term, is -6. So you would draw all those points, -3, 1/2, 1, and 2, and y equals -6. You're going to start at quadrant 2, so start here, go towards your intercept. We're crossing the intercept, curling up to get to this through the 6. Back up, we go through 1/2, through 1, curl around through 2, and extend up to quadrant 1. That is the graph of this degree 4 polynomial. Last but not least, example 3 asks you, or tells you that you've got a cubic function that has zeros of 4, -2, and 3, and a y-intercept of 6. Determine the equation. So you guys know that in factored form, we get all of the zeros. So you'll see here what I did was I used these zeros to create my factors. 4 would be a factor of x minus 4, -2, x plus 2, 3, x minus 3. But I could have an a value. I could have a leading coefficient that's something other than 1. If I know that the y-intercept is 6, means I know that 0, 6 satisfies this equation, I can solve for a. So in this case, I plug in x equals 0, and I plug in y equals 6. When I multiply this through, I get 24a equals 6, so a must equal 6 over 24, which is 1/4. This is really similar to what we were doing in the radical equation unit when we were figuring out some of our transformations and then plugging in a point to solve for a or b values. Very similar. Now it asked for it in standard form. That means this would be factored form with 1/4 up here. I've written it here. 1/4 times all my factors. So then I'm just going to distribute all of this through. When you multiply all of this through, this is your result. And then you're going to gather your like terms and multiply each by 1/4. So your final function is right here. It's a little bit messy with some fractions, but that would be in standard form. That wraps up how to graph and write equations for these polynomial functions. Practice, practice, practice. This graphing can be a little bit tricky, but the more that you try, the more it will make sense.